All right, so today basically the theme is, I couldn't really come up with a cohesive theme, so I call it array manipulation. But basically by that I mean bitwise operations, prefix sums, and DP. That's how I've decided to kind of group them together, which I think works, and what I say goes, so deal with it. Okay. Oh, I forgot this doesn't work. I need to use my arrow keys.
Exactly, you should start.
Yeah, hold on. Technical issues. This doesn't work.
Press space.
I'm trying to get rid of my cursor. I don't want the cursor there. There we go. Okay, bit manipulation. So we went through this very briefly in the very first workshop, if any of you remember that. But basically, I hope you guys all know binary stuff, computers, that kind of stuff. Very gist of it, numbers represented as ones and zeros. We can basically do things to those ones and zeros on like a fine-grained level, which is very useful in some situations. And so that's generally referred to under like the umbrella category bit manipulation. And so like the most basic form of these are your bitwise operations. So I assume most of you are pretty familiar with logic gates. So you've got your standard ones, the most common ones are really AND, OR, NOT, and XOR. There are others like NAND and NOR, but you can kind of combine these to get them. So these are all the ones you really need. And so in most languages, including C++, these are how they're represented. So NOT is usually with a tilde, AND is with like a single ampersand, OR is with a single like vertical pipeline operator, and XOR is with like the kind of like your exponent operator. So that's how it is in C++ and most other languages, I believe. One key thing to note is that it's very similar to like your Boolean expressions. So like AND is 2 ampersands and OR is 2 pipes. The difference between one of the symbols and two of them is 2 is if you're doing a logical comparison. So like if this or this is true. A single one is you're doing a bitwise operations. This is the mathematical like computation of computing these two numbers bitwise ORed together. So this is just an example of tables. I just came up with two random numbers X and Y in binary. And this is what the results of those operations are. So have a read through them, make sure it all makes sense. With NOT, you're flipping all of the bits, which is simple enough. With AND, anytime that both bits in the same position are true, the output bit is true, but if only one of them or none of them are true, then the output's 0. With OR, if either one of the bits in that position is true, then the resulting bit is true. And with exclusive OR, it is exactly one of them is true. So I hope that all makes enough sense. If everyone said I read through the table, call out if you've got any questions or if I've made a mistake, which I might have because I typed this out quickly. But yeah, is that all good? Nice. The next thing is shifts. Shifts are very useful. It's used with these like, it's annoying that it's the same operator in C++ as like your input and output streaming stuff. But basically like greater than or less than signs, two of them is a bitwise shift. And so it's essentially equivalent to dividing or multiplying by a power of 2. But it's a nice compact form and easy way to think about it. So with this number, again, just a random binary number, if you right shift it by 2, you're basically shifting all the bits one position to the right, and you're cutting off any that are like go out of bounds, essentially. So these two last bits, they're essentially dropped off because you're shifting them past the end, and everything else moves over 2 positions to the right. Does that make sense? And so that's essentially equivalent to dividing by 2 to the power of 2, or 4, and then just like ignoring any remainder, which is what this bit is when you're just getting rid of that. And the opposite is left shifting, so then you move everything 2 positions to the left. There's 2 new positions now. Instead of cutting 2 off, you just add 2 zeros. And so it's the same as multiplying by a power of 2, in this case multiplying by 4. Does that make sense? Cool. So that's how you can like manipulate integers from kind of using their binary form, but you also want to be able to access different parts of the binary because usually you'll still use like just regular integers in whatever programming language you're using. You won't have like a specific binary type. I keep forgetting I don't have a arrow. But you can do that with bit masking. So a bit mask is basically kind of a mask, if you've used like Photoshop or something, you know, like a mask how you use to like extract layers and like different parts of it. Bit masking is the exact same thing where you're using like a specific kind of, it's what's called a mask to extract specific bits. So basically a bit mask is really just another number, a binary number, it's ones and zeros. And most commonly you'll use the AND operation, a bitwise AND. And so if you do an AND between some number and your bit mask, then it will extract essentially all of the bits that where the bit mask is equal to 1, and everything else will be set to 0. And so the easiest way to use that is just ANDing it with the number 1. And so you can think of 1 as just a series of zeros with the 1 right at the end. And so that's going to make all of the other bits to the left equal to 0, because anything ANDed with 0 is 0. And it's just going to essentially extract the least significant bit. So if your binary number ends in 1, this will be 1. If it ends in 0, it'll be 0, which then is easy. You can treat it as essentially an equality or comparison. So you can check if it's 1, it's like true, is the bit set. If it's 0, it's not set, false. So yeah, that's the basic one. Sometimes you also want to check other bits, so not necessarily just that least significant bit, which is kind of the same as checking if it's even or odd. You might want to know if the 4th bit from the right is set. And so to do that, you can just create your own bit mask here. And so that's shifting 1 to the right by I places. So then you've got essentially a bit mask that's 0, 0, 0, 0, 0, etc. 1 in the 4th position, and then the rest are zeros. And so again, ANDing that will give you 1 if that bit was set, and 0 if it wasn't. These are just two kind of somewhat common tricks. You don't really need them too often, but sometimes they're quite useful. You can get the least significant bit of a number by ANDing it with the negative version of itself. If you've done anything with 2's complement representation, you can kind of, if you play around with it with pen and paper, you can figure out why. You don't really need to understand it, but it is sometimes helpful to remember that this will give you the least significant bit that was set in the number. And you can also remove the least significant bit. So, and also by a least significant bit, I mean the first bit that's set to 1 from going right to left. And you can also remove it by ANDing it with itself subtract 1. Again, if you play around with it on paper, you can kind of see why, but you don't really need to worry about that too much. Okay, and then bit sets are probably the most useful thing and what bit manipulation is most commonly used for, which are basically, it's in the name, it's a set of bits, essentially. So in C++, if you remember back, this was also probably in the first workshop, that integers, depends on the hardware, but usually 32 bits wide, and longs are usually 64 bits wide. And so bit sets are usually, you'd only store up to 64 because that's what makes sense in a long. But you can store up to combinations of up to 64 elements. So a set, a very efficient way of storing a set of sum or subset of up to 64. And so for example, that binary number, 10010, would represent a set containing elements with indices 1 and 4. When I say indices, with binary numbers it's a bit weird because we still zero index it usually, but we talk about going right to left because your least significant bit is your rightmost one. And that's just useful because of back here, you can just use this I gives you the index if you shift it to be able to look at that index specifically. So that would be index 0, that's 1, 2, 3, 4. So because indices 1 and 4 have a 1 in the binary number, the set does contain those elements and the rest would not be in the set. Does that make sense? No questions so far? Nice. There's also C++ has a type in the standard library. There's a bit set type and you have to give in n, which is the number of bits you want to have in your bit set. So you can have larger than 64 there. I don't think I've ever used this type because if you've got larger than 64 elements, usually you can just use a different data structure when the main thing that makes bit sets useful is if they're really compact and can be stored inside an integer. And so I just tend to use integers most of the time. But bit set does have some nice operations, especially those logical bitwise operations and a few other ones, you can count the number of bits that are set. There are a few nice things there. You can look at it on the documentation if you like, but I don't think I've ever used that. So don't worry too much about it. Probably the most useful application, apart from DP, which I won't go into bit set DP today because that's a very advanced topic, but it's good to know it exists. But probably the simplest, most useful application of bit sets are to iterate through all possible subsets of a small number of objects. So usually that's quite an annoying thing to do. Off the top of my head, I probably couldn't figure out how, if you've got, say, 30 objects, how do you find every single subset of them and then do some kind of test on them if you've got a question that requires that. But bit sets are a really easy way to do that because if you think about every number in binary form from, say, that's got 10 bits wide in it, every possible binary number just gives you that combination, every possible subset, because you have to have every possible combination of 1s and 0s 10 bits wide. And so that's a really nice way of doing it. You can iterate, so I would be a set, I equals 0, would be a set with nothing in it, because everything's set to 0. 2 to the power of n, so if you've got 10 objects, 2 to the power of n would be the first number that is like more bits wide than n, so that would be like n plus 1 bits. And so less than that gives you every possible number that is less than or equal to n bits. And so iterate through all of that, and then that just gives you a bit mask, or bit mask or bit set, which tells you which elements are currently in the set, and then you can use your bit manipulation stuff from the previous slides to check which elements are currently in it. So usually you just iterate through every position and check if the bit is set or not. And so that's very useful for combinatorics questions. And it's often used with dynamic programming to store a subset as well, but that's quite complicated. So I won't go into that, but we will go into basic dynamic programming towards the end. That's kind of everything about bit sets. I've got a simple example of bit manipulation question here, I think. Yeah, so single number. So you've got a non-empty array of integers, and every element appears exactly twice, except for one which appears once. And you need to find that number. And so this would ordinarily be quite a simple question, but it also says it needs to be linear time, which is fine, but constant space, which is the tricky part. Have a think about how you might do this. I haven't really explained it. It's kind of one of those properties of bit manipulation that is useful. I didn't explicitly say it, but if you know your bitwise operations, that might help you out. So have a quick think. Does anyone have any idea what bitwise operation might be useful for this one?
Could you use XOR?
Yeah, so because XOR, so again, XOR is exclusive OR. Since it kind of undoes itself, because if you bitwise together 1 and a 0, it'll give you 1. But if you bitwise 0 and 0, it'll give you 0, and 1 and 1, it gives you 0. So any bits that are the same are kind of undone. That means if you do a bitwise XOR of a number with itself, it will always give you 0. And so if you do an XOR on every number in this set, all the pairs will cancel that to 0, and it'll leave you with that one single number. And so that's what I've got there. And so it's a nice and easy solution. Does that make sense to everyone?
You can say no, by the way.
You can say no. Do you have any questions about anything in particular?
You do like a small set on the board, like a couple numbers to show, I guess.
Yeah. Do you want to like me to run through like an example of that?
Yeah, sure.
Yeah. Do we have a whiteboard marker? Here we go. Yeah, so if you think about, I'll keep it small numbers, so we'll do like 3, 3, 2, 2, 5, 5, 7. So in binary, that would be 1, 1, 1, 0, 1, 0, 1, and 1, 1, 1. And so when we do the XOR, so what this is doing, basically keeping starting at 0 and then XORing every number into that result. So start 0, XOR with 3, so that just gives us, I'll do 0, 1, 1, because that's just, we start off with just 3 essentially. Good so far? If I'm going to change the order of this, so I might go left to right and I'll do the second pass. So let's do 2 next. If we XOR that with 2, then we get these are the same, so we get 0. These are the same, so we get 0. These are the same, we get 1. Different, so we get 1. Yep. And so that'll go through. I won't do all of them actually, but if we go back to 3 now, then so that was 0, 1, 1. This is going to end up being 0, 1, 0, which then leaves us with 2, because the 3s have kind of cancelled out. And you can kind of see that if you think about doing 3 directly with itself, because since all the bits in each position are going to be the same, they all end up being 0. And so that kind of happens for every single pair, and that leaves whichever one doesn't cancel out. Does that make sense?
Yeah, that makes sense.
Yeah. All right, so yeah, that's everything for bit manipulation. Does anyone have any questions about binary stuff? Cool, okay. Prefix sums. This is a very wordy slide, but hopefully, lots of slides here are wordy, but there's a lot of kind of examples I've tried to bake in. So say we got an array. I just come up with an array of random integers. They are all positive. They don't need to be positive. I just happen to make them that way. There's a lot of times we want to compute something called a range query, which is basically we're given a set of queries about a range of items. And so this is a very broad term. It comes up a lot in a lot of problems. The simplest kind of example of a range query is, given a range of numbers, find the sum of every number in that range. So for example, indices 3 and 7, 0, 1, 2, 3. So from 0 to 4, 5, 6, 7. From between this 0 and 8, we want to find the sum. So that's one particular range query. Usually we'd be asked about a bunch of range queries. You might be given like a list of inputs, or an array, a list of inputs for different ranges, and you need to find the whatever it tells you, in this case the sum. Does that make sense so far? Yeah. So it's easy to calculate a range query with brute force. So in this case, the sum, we can just go through elements 3 to 7, we can add them all up, O of n where n is the length of the range, nice and easy. The issue is if, like I mentioned, instead of one range, they give us n ranges, then now this is going to become n squared because we don't O of n work for each of the range queries, which often is going to be too slow for the problem, because otherwise it would be quite easy. So one thing we can do is use what's known as a prefix array, or prefix, in this case, prefix sum, which is essentially just a cumulative sum. So we start at 0, and then we do a cumulative sum of every element in the array. So we add 1, then we add 4, then we add 8, then 0, then 4, etc., etc. Does that all make sense? And so now the range query sum is of 1, because what we can do is we can go to prefix sum 8, which basically gives us the sum of all the numbers from the start of the array, and then subtract prefix sum at index 3, which subtracts off the ones that we don't want at the start, and that leaves the sum of that range in the middle that we wanted. And so that's just one subtraction. That's now O of 1, so doing n of those is now O of n, which is a big speed up. Does that make sense? Yeah. So prefix sums are kind of the most common one that will come up and the easiest one. But you can do prefix arrays of different operations. So for example, subtraction would also work. The key thing for whether you're able to use this technique or not with an operation is it needs to be able to be undone, because if we want a sub-range in the middle, we need to be able to have that operation all the way up to the end of the range, but then subtract off the bit before the start. Or in this case, it's subtract. In another operation, it will be to undo it. So multiplication, like if you want to find the product of a range, that is possible with a prefix array, but it is tricky. Can anyone think of why might that be the case? Yes?
Zeros are a bitch.
Yes, zeros are a bitch. So we can undo multiplication, which is that's division, but zeros they don't like division. So yeah, you can kind of there's ways you can use zeros as an edge case, and you can make notes of them and use sets and stuff. It's kind of just a pain. But yeah, the easiest way to do it is just to have no zeros, which is often the case. If this is the intended technique, they'll often just say positive only numbers, and you won't have to deal with zeros. Definitely nothing in Div B would ask you to do a multiplication prefix array with zeros in it. That would be ridiculous. There is actually one other reason though why multiplication is tricky. Zeros are the main one, but can anyone think of something else? Yes. Do you want to elaborate on that a bit more?
Yeah, like a long becomes...
Yeah, so running out of size, especially in C++, you've got 64 bits. If you're multiplying 10 to the 5 numbers together, that's going to get bigger than 64 bits, assuming that they're all decently sized. And so it is still possible, and this is something that actually I'll touch on next workshop, but you can basically, if you've done a lot of LeetCode questions, you would have seen the ones where it's return the answer mod n, if it's really big. You can kind of do that with this, where you can kind of do a multiplication prefix array, but you do it mod n, and then there's a way you could actually do a modular multiplicative inverse, which is essentially equivalent to division. I will go through that next workshop, don't worry about that for now. So again, XOR is possible with this. So again, because we did talk here about how XORing something with itself undoes it, so you can undo XOR, it's just by doing the same thing again. And so that'll work, but not bitwise and. Can anyone have a guess?
Because 0 and 1 comes to 0 and 1 and 0 comes to 0, so it's you can't reverse that?
Yeah, you can't really reverse and, because if you and say 10 numbers together, there's no way to undo 9 of them and figure out what your last number was. But if you XOR 10 numbers together and you do the XOR with 9 of them, it'll leave you with the last one. Okay. Yeah, and I don't have an example there because that was kind of the example. There is an easy LeetCode at the end, which is basically just implement this example. So I'll get you guys to have a go at that once we go through dynamic programming, which is the bit that everyone's been talking about, I think. So dynamic programming is scary to some people, but it's very useful. If Alec was here, for those of you who know Alec, he'd complain that it's actually not the real dynamic programming, it's a maths term, but programmers use it differently. I'm going to talk about it in the programmer way because that's what I know. But basically, it's a method of, it's usually used to speed up problems that can be solved by brute force, where in brute force there would be exponential time operations, but you can usually speed them up to linear. And the reason why this is possible is because usually it's in the case of problems that could be solved recursively, where there's a lot of subproblems. And the subproblems are the same when you get down to the smaller cases. So you're computing a lot of the same subproblems, which would take a lot of time if you were to compute them all from scratch. But if you just store the result of the subproblem, you can just look it up in a constant manner. Does that kind of make sense so far? Yeah. So it's usually applicable, like I said, for recursive problems where there's overlapping subproblems and lets you solve them in linear time instead of exponential time. There's a few ways to implement it. The easiest way is top-down, which is also, sometimes you'll see memorization is the fancy term for that, and then caching is the non-fancy term for that. So it's usually an easier way to implement it because you can just take a recursive function that you've already implemented, which might be exponential time, and then you just add a few extra lines that first check whether you've already calculated a result, and if you have, then you return it. If not, then you do your regular recursive stuff, but before you return the result at the end, you just store it. And so usually you'd store it either in a hash set or an array or something like that where you can look up in constant time. You can also do bottom-up, which the fancy word is tabulation. Usually it's hard to implement, but it is often faster and more memory efficient because, first of all, it's not recursive, so you don't have that memory overhead of having to stack frames for recursion. And also, sometimes, if there's a nice pattern in which the subproblems need to be reused, sometimes you get to a point where you know for sure that you won't need any older results, and so you can kind of overwrite them, which lets you often improve the memory in asymptotic complexity. So it might bring the memory down from n squared to O of n. I'll go through an example of that in a second. So the simplest example is Fibonacci numbers. So I hope everyone's familiar with the Fibonacci sequence. You start with 0 and 1 or 1 and 1, and then you basically sum the previous two numbers together. It's a nice example because it's quite simple, but it's very easy to implement a function like this, so I've got my base case for the recursion. If it's 0 or 1, essentially return 0 or 1. If it's not 0 or 1, then return the sum of the previous two numbers. And so that's a very nice way to implement it. Unfortunately, it's extremely slow because if you think about the number of operations you're doing here, if you want to calculate the nth Fibonacci number, then each time you make a call here, it's going to split it into two subproblems, which are essentially one smaller size. An extra -2 here instead of -1 won't make a difference because it's still going to do n iterations down if you think n and n over 2 are of the same order. So essentially, you've got n layers of recursive operations you're doing, and each layer you're splitting the problem into two smaller problems. So you're going to end up with 2 to the n problems on the last layer. And so if you add up all the problems, it'll be on the order of 2 to the n. Yes?
With this recursion pattern, isn't the tree repeating a lot of the recursive calls?
Yes.
So you have let's say 5, and then 5 will appear somewhere else and down the tree. So
yes, that's exactly right, which is why this is one case we can use DP. So I'll actually draw that out to make it a bit clearer. So basically, if we're finding, so I've got the 10th Fibonacci number there. So if we start off with 10, that'll go into 9 and 8, and that'll go to 8 and 7. This will go to 7 and 6. I'll stop there. But basically, you can see this is what the n in the call to the function each time. So you can see that we're doing 9 once, 10 once, but we're doing 8 twice. Once we get down to 6 and 5, we're doing 6 3 times. And so you're just doing a bunch of work that's the exact same as you've done previously, and it just slows it down a ton. Does that make sense? Yep. All right. So this is a memorized solution that'll speed it up. So this one we said was 2 to the n time complexity. This is now linear. And so the main difference is we've got this memo, or for short for memorization, array here. So this is just, I've set it to 100, so this can only store up to 100, but you could make this as large as you need. And it's storing the result for the nth Fibonacci number at index n. And so initially, we're just initializing it to -1, so we don't know what the result is for any of the Fibonacci numbers, except, did I put in, okay, I could have put the base case here already, because we know that 0 and 1 are 1, but I'm just handling that here. So then in our Fibonacci function, this bit is the exact same as the exponential solution from before. We just added 2 extra lines. So the first one is if the nth number is not -1, which means we've already calculated it, we just return it immediately. So this line converts that particular function call to just an O of 1 call, because you're just looking up the index in the array. And then if it's not there, we do our regular calculation of it, and then before returning, we just store it in the memorization array. So that way, if we ever have to do this n again, it'll just see it in there, and we'll just return it immediately. Does that make sense? Yep. And so now, time complexity is down to linear. We're initializing this array, which is linear in the maximum number of elements we want to store. And then because in the Fibonacci calls, we can only have to do like this work up to once each for every number n. So if we've already calculated, we're just returning instantly. So that way we're only actually calculating the result the very first time we do it, and that'll be up to n times at most. Yes?
Could you just do this with a map instead as well?
Yep, so a map would work fine. You could use a map from int to int, and so then you can just look it up if it's a map, like the specific map type in C++, that'd be logarithmic lookup, because it's like a red black tree. You could also use a hash map, that'll work too. Any of those are fine. The main advantage of a vector is it's just faster and uses less space. But all of those would work for a solution, yeah. Any other questions? Cool, so this is the bottom-up solution that I wrote, where instead of doing it recursively, we're doing it calculating from n, counting upwards from 0 instead of recursively down from n. So essentially, I'm keeping this last number. Yeah, okay, so this is essentially storing the last number that we calculated, well, the last index that we calculated in DP. This isn't necessary, it's just a small optimization I did. So starting at 1, because we haven't calculated any of them yet, except for, or we calculated 0 and 1, I put in just initialize them for the base case. So whenever we call this Fibonacci function, again, the first bit's the same. If we've calculated the result, we're just returning instantly. And then this is why I did that last, because I'm just starting the next one that we yet to calculate, and then I'm adding it, I'm calculating that one by finding the sum of the previous two, and then we keep doing that until we get up to n, and then I'm updating last just so we never recalculate those ones, and then returning that number. Does that one make sense? So we're always still doing the same thing. We're returning anything we've calculated before, but if it's bigger than anything we've calculated previously, we just keep going from where we left off, essentially. And making sure to store all of those in the array as well. All good? Cool. And so I mentioned before that with dynamic programming, if you do it bottom up like this, often you can eliminate like a order of magnitude of space consumption. In here, because we're only ever using the previous two numbers, so I minus 1 and I minus 2, we don't actually need anything like more than 3 numbers ago if we're going up. This one also, because I've got this like global array, this could be used for multiple like different calls to this number. But often in competitive programming, we're only calling the function once anyway, so it's only the first call that we care about and for the subproblems. But there's just one distinction to note. But we can save memory there if we're only calling that function once by getting rid of that array altogether, and instead just storing those last 2 numbers. So I've got last and current, initializing them to the base case. If it's a base case, just returning it. And then we go upwards still until we get to n. And then we calculate the next number, which is the sum of the previous 2. And then we just overwrite so that the last number is now what was previously the current one. The current one's this new current one. We keep going until we calculate the nth Fibonacci number and return that. So we've gone down from linear space to constant space. Does anyone have any questions?
Does that apply to memory? Like complexity? Like does it reduce
Yeah. So
the stack as of like when you recursively calling something? I'm assuming that the stack is taking way too much space.
yeah. So if we go back to the brute force one,
Yeah.
this would also the way the recursive tree works is because you're kind of like following down this tree essentially on the stack calls.
Yeah.
In the worst case, the memory used up by the recursive stack is only going to be the height of the tree, which in this case would be n. And so you kind of just, it is less memory altogether, but it's the same complexity for like these solutions. But then this last one, that brings it down from O of n to constant numbers, which has got 2 integers. So yeah. Anything else? Great, because my throat's starting to die. So I've got some questions to try out.